Hello, in this video, I will cover relative number of protons in each set, which infers the integration. This will be a fairly short video, but just covering the concepts of what integrals are and integrations are. And so this continues our proton NMR videos. This is the third installment of four plus an overview, so 5 total. All right, so here we are, the integral. The integral is the relative number of protons in each set. Exchangeable protons may not show up in the 1H NMR, so there may be other protons in the structure that just aren't showing up in the NMR. So things like OHs and NHs, so protic hydrogens, may not show up in the NMR if the solvent that's being used to dissolve the compound of interest is also exchangeable in terms of a deuterium. Okay. Deuteriums don't show up in the proton NMR. So if you have an alcohol and you're taking the NMR in deuterated water, that alcoholic OH is just going to exchange. So again, you may not see all the peaks if there's those type of hydrogens, but otherwise you should. And the integral should be some relative ratio of protons responsible for each unique signal. All right, so I got a couple of examples here, and these are going to be constitutional isomers of each other. I chose 2-pentanone and 3-pentanone just to kind of show the concept. The integrals refer to the relative ratio of protons in each unique set. Each unique set of protons produces a peak in the spectra. So let's assume that we had and we'll do 2-pentanone first. Peak A, or set of hydrogens A, set of hydrogens B, set of hydrogens C, and set of hydrogens D. And you can see how many hydrogens are responsible for peak A and how many are responsible for B. If I tell you that these 2 hydrogens for B, those are going to be enantiotopic, so they're NMR equivalent, but they're different than C because they're connected different, right? This carbon is next to a carbonyl. This carbon is not. So that's just a different environment. So I know that the peaks for B and C are just different, right? Homotopic. And then this CH3 is different than this CH3. This is not a carbonyl. This is. So you can just see that there's just a different chemical environment. So A and C and D have different CH3 groups. So there's 4 unique signals. And the integral, let's say I knew this integral and I set it to 3, then it should set all of the other integrations accordingly to the relative number of hydrogens in the other signals. So for B, there's 2 hydrogens, C, there's 2 hydrogens, and D, there's 3 hydrogens. So you can see it's a 3 to 2 to 2 to 3 ratio of protons in those 4 unique signals. Okay. All right, because there's no symmetry element present in the molecule, again, that's why you're getting the 4 unique NMR signals. Now, if you go to a different constitutional isomer, if you have, let's see here, if you move the carbonyl over 1 position, okay, now you've got 3-pentanone, and now you've got symmetry introduced here. And so it kind of basically cuts the molecule in half here. And so now you're only going to see 2 unique NMR signals. You can convince yourself of that by doing a replacement test and noting that. I'm telling you there's 2 signals. Okay, so I've labeled each peak A. There's 6 hydrogens total for the peak that's giving rise because of those. And there's 4 hydrogens responsible for peak B. Okay, so if you didn't know the integral of, say, that, and you guessed and you said it was 3, then that would be 2, right? Because that's a 3 to 2 ratio. If you multiply that by 2, that's 6 to 4, the same ratio as 3 to 2. So it's a relative ratio based on the number that you've assigned to one of the integrals, assuming that you knew one of them. And then it sets all of the other ones relative to that. So that's just a little bit of a tidbit about integrations. It's a ratio, okay, of the number of hydrogens in one peak relative to the number of hydrogens in the other peak. Here is the NMR for each of the two structures we were looking at here. So you can see once again, you've got 4 signals here, right? And you've got only 2 signals here. And so the integral then here would be 3 hydrogen. You would see 3, right? The area under the curve is 3, and C, that area is 2, and A, that area is 3, and for B, the area is 2. And so those are the integrals that you would see if the NMR was integrated for you. And for the next compound here, you have A, there's 6 hydrogens that give rise to A, and B, there are 4 hydrogens. So once again, a 6-to-4 ratio is the same thing as a 3-to-2 ratio if you reduce those numbers down, but you still have to have, or you still want integrals that represent the molecular formula, right? And so let's look at those. You have 1, 2, 3, 4, 5 carbons in the top case. So we've got C5. Count the number of hydrogens, and you got 3, 5, 7, and 10. And then we got an oxygen. And so if you count up the integral numbers, that tells you how many hydrogens total in the structure. And that's the idea, because the signals are due to the hydrogens. All right, so now let's go back to a previous structure from lecture 42. Let's look at D. And now let's go ahead and put the integrations in here. And so we're going to have basically a 3. So I'll just write it left to right. We have a 3 to 2 to 2 to 2 to 3 integral ratio for the 5 unique signals that you're seeing, right? And so E, and I've color coded it for you, so it should make it pretty simple. You haven't learned about splitting yet, and that'll come on the next video. And so A is going to be 3 hydrogens. B, that's going to be 2 hydrogens. C will be 3 hydrogens. And we've got 2 hydrogens giving rise to peak D and 2 hydrogens giving rise to peak E. Can you assign the splitting pattern? That would be the next video coming up. So the next thing here, can you assign the multiplicity, which is the splitting pattern, for each signal? Okay, and that'll be coming up. So let's go ahead and end this video, and thank you for your time.